Hey everyone, and welcome to The Explainer. I am so thrilled to have you all here today because we're taking a really fascinating journey under the hood of artificial intelligence. I mean, we all know the magic trick, right? You type a prompt into ChatGPT, and basically instantly it spits out this highly detailed, coherent answer. But what's actually happening in those few milliseconds? How does AI process information so incredibly fast? Whether it's running on some massive server farm or just sitting right there in your pocket on your smartphone. Well, we're going to unpack the fundamental mystery of that engine right now. So how does AI actually work? It's the million-dollar question, right? It's what bridges the gap between our everyday experience, just typing in a simple prompt, and the incredibly complex background machinery that powers the response. At its core, the algorithms that make up AI are just breaking down complex tasks into totally manageable operations. But, well, there is a catch. Okay, let's dive into this. Consider this your friendly, playful warning. We are entering the realm of mathematics. Lots and lots of math. But hey, don't worry. I promise to keep this really structured and completely accessible. We're going to look at this like a massive logical assembly line, building from the ground up, so you can clearly see the mathematical foundations that power this whole system. Here's our roadmap for this mathematical assembly line. We'll be hitting 1. Converting data into math. 2. The neural network brain. 3. Forward and backward propagation. 4. Upgrading the training process. 5. AI evolving and battling. And 6. Compressing and protecting AI.
All right, let's jump right into section 1, converting data into math. So before an AI can do literally anything, it needs raw materials it can actually understand. And just like everything else in a computer, it all comes down to binary, ones and zeros. AI is absolutely no different. Take a photo, for example. When an AI looks at an image, it doesn't see a pretty picture. It completely converts that visual data into numerical matrices. Just imagine a giant 2D grid where every single pixel becomes a number in a massive matrix. Once the data is in that format, it undergoes these really complex mathematical transformations. Through constant multiplication and addition across these grids, the AI starts doing things like edge detection, pattern recognition, and feature extraction. The entire foundation of AI totally relies on these layered mathematical algorithms working together to turn a picture into pure, raw numbers.
Which brings us to section 2, the neural network brain.
And this brilliantly illustrates the core of the whole thing. Now that our data is chopped up into tiny numerical blocks, it's time to enter the actual machinery where this math gets processed. The absolute core building block of this entire architecture is the node, because neural networks mimic human brains, right? So, when our matrix data enters the network, it hits an input layer and then flows into what are called hidden layers. Inside these hidden layers are these interconnected nodes. Think of a node as a little worker. It takes incoming values, multiplies them by specific weights, adds a little bias term, and then processes it. It's basically a massive, incredibly fast factory doing constant multiplication and addition.
But after those weights and biases are calculated, the node has to decide what signal to pass on. That's where it applies an activation function. These are absolutely vital because they introduce something called nonlinearity. That's the secret sauce. It's what allows the network to learn incredibly complex patterns instead of just drawing boring straight lines. Two common ones are ReLU and sigmoid. ReLU is super straightforward. It passes positive values through completely unchanged, but if a value happens to be negative, boom, it instantly sets it to 0. Sigmoid, on the flip side, squashes any value you give it into a tiny little window between 0 and 1. And that math defines exactly what signal gets passed to the next layer down the line.
Moving right along to section 3, forward and backward propagation.
So we've got these nodes performing math and passing signals, but how does this machinery actually, learn? Well, first we have forward propagation. Think of this as the forward flow of the factory. The network takes those input values, multiplies them by their weights to create weighted sums, and passes them through those activation functions we just talked about. The data flows forward, layer by layer, until it spits out an answer at the very end. But here's the thing, initially that answer is almost certainly wrong.
And that's exactly where backward propagation steps in, to save the day. The network looks at its final answer, compares it to the correct answer, and calculates the exact mathematical error. Then it sends that error backward through the network. It uses this amazing calculus concept called gradient descent. It essentially uses partial derivatives to calculate exactly how small changes in every single weight contributed to that big final error. Then it updates those weights in the direction that will reduce the error for next time. It does this over and over and over, guided by a learning rate that controls the size of the adjustments. If the learning rate is too large, the learning gets totally unstable. Too small, and progress is agonizingly slow.
It's this massive, delicate, balancing act of calculus, but thankfully, the computer does all the heavy lifting for us.
All right, let's look at Section 4, upgrading the training process.
So, calculating all those partial derivatives across millions of nodes takes massive computational power. Let's look at the incredible engineering techniques used to upgrade this process and make the AI factory fundamentally faster. See, as data flows through a network, its statistical properties constantly change, which forces each layer to adapt continuously. Engineers actually solve this bottleneck with something called batch normalization. Basically, it standardizes the inputs to each layer by mathematically subtracting the mean and dividing by the standard deviation. By stabilizing the learning process this way, engineers can crank up the learning rates, which can actually reduce the total training time by up to 14 times. That is a massive efficiency boost.
But there's another hurdle. Just like a team of people, a neural network might accidentally rely on just a small group of nodes to do all the heavy lifting. And if those specific nodes fail or get confused, the whole system crashes. To prevent this, engineers use a brilliant, kind of crazy technique called dropout. During training, the system literally just randomly shuts off portions of the network. It just turns them off. This forces the other neurons to step up, co-adapt, and compensate for the missing units. It essentially simulates training thousands of different, smaller neural networks simultaneously and then averages their results. This vastly improves the AI's ability to handle brand new, unseen data.
So the crucial point is, we don't always want to build these massive factories from scratch. Training a network from zero takes massive data sets. We're talking millions of examples and literal weeks of computing time. The much smarter upgrade is transfer learning. Transfer learning takes a pre-trained model that already knows how to do basic math, like detecting edges or shapes from millions of images, and it just replaces the final layers. This means you really only need hundreds of examples and a few hours to fine-tune the AI for a highly specific task. It's a total game changer.
Which leads us into Section 5, AI evolving and battling. Now that we have these highly optimized, super fast learning networks, things get really interesting. How are these AI models structured to actively compete against each other or even creatively design themselves? Have you ever wondered how AI generates those stunning pieces of artwork or composes music? It's very often done through generative adversarial networks, or GANs. Think of it as a mathematical minimax game where two neural networks are locked in a battle. The generator network tries to produce increasingly convincing fake data, while the discriminator network acts like a detective actively trying to detect those fakes. The generator is constantly trying to minimize the exact same mathematical value that the discriminator is trying to maximize. This endless, intense competition is exactly why AI went from generating those weird, blurry faces a few years ago to producing near-perfect, award-winning art today. But as you can imagine, designing these dueling architectures by hand is incredibly tedious for human engineers. Enter neural architecture search, or NAS algorithms. Instead of a human building the AI step by step, NAS algorithms systematically evaluate thousands of potential structures all on their own. And honestly, even more fascinating is neuroevolution. This actually entirely replaces the traditional gradient descent we talked about earlier. It evaluates a whole population of neural networks, picks the best performers, and mathematically mutates and crosses over their genetic material, their weights, and their architecture to evolve entirely new, highly optimal networks, totally without human intervention. It's literally evolution inside a computer. And finally, let's wrap up with Section 6, compressing and protecting AI. So we've built this incredible, self-evolving mathematical engine. But zooming out for a second, how do we actually fit these massive factories into the devices in our pockets? And how do we keep our data secure while using them? When AI is making high-stakes decisions in, say, healthcare or finance, we absolutely need to know why it made that choice. That's explainable AI. It uses methods like SHAP and layer-wise relevance propagation. These tools trace decisions backward through the math to quantify exactly which input features, maybe a specific word or a tiny part of an X-ray, actually influence the AI's choice. And for privacy, we have federated learning. Instead of sending your personal, sensitive data to some massive server, the global AI model is sent down to your device. Your phone trains the model locally, and then only sends the updated mathematical parameters back to the central server. So your raw data, it literally never leaves your device. Now, what's really interesting about this slide is how we solve the actual size problem. Engineers use something called quantization. See, standard neural networks use high-precision 32-bit floating-point numbers. They're huge and take up tons of memory.
But by transforming those giant numbers into low-precision, 8-bit integers, we can mathematically compress the model's size by 75% or even more, with barely any loss in accuracy. This is exactly how we're able to deploy these incredibly powerful AI models onto resource-constrained devices like your smartphone or tiny smart sensors.
And as these compressed models are just sitting on our devices, they actually continue to learn through self-supervised learning. This totally bridges the gap between supervised and unsupervised learning. The network creates its own supervision signals straight from raw, unlabeled data. It creates what are called pre-test tasks. For instance, it might mask out parts of an image and basically force itself to predict the missing pieces. Or it looks at a block of text and predicts the very next word in a sentence. Yeah, exactly like the autocomplete on your phone. This allows the models to learn from billions of words or images entirely automatically, without humans needing to meticulously label a single thing. While we've journeyed all the way from ones and zeros to complex matrices, through the calculus of gradient descent, and all the way to compressing AI down into neat little boxes on our phones. But I want to leave you with this really provocative quote directly from our source material. Compression isn't enough to save you when you're running out of space, and everyone runs out of space, including Google themselves. As our mathematical AI engines just continue to evolve and grow and consume more and more data, what happens when we hit the absolute physical limits of our hardware? It's definitely something to chew on as you watch this incredible technology continue to unfold. Thank you so much for joining me on this explainer, and I'll see you all next time.